Okay. Anyway, we should probably get started now. Let's do that. So, okay. Thank you everyone for coming today. So today we have Jamol Pender, who's Associate Professor in Operations Research and Information Engineering at Cornell University. He got his PhD with Bill Massey at Princeton. He's won several awards. He has a Ford Foundation Fellowship, NSF Career Award, MFI Career Award, as well as several teaching awards. I know Jamal for doing a lot of excellent work in kind of theory of open and closed queuing networks, but also as someone who's very happy to kind of dip his toe into different application areas. So that's what we're going to be seeing today from Jamal's talk on beyond safety drivers, staffing a teleoperations system for autonomous vehicles. So thank you very much, Jamal, and please take it away.
Okay. So first, thank you guys to have me. This is, I think, been a staple in the applied probability community, having this SNAPP seminar. So I'm certainly delighted to be one of the speakers. And before I begin today, I'd like to acknowledge the two most important people responsible for this work. And the guy on the right was my former graduate student, Andrew Daw, who's now making millions at USC's business school. And on the left, we have Robert Hampshire, who's now the Assistant Secretary for Research and Technology in the Department of Transportation. So he actually works for President Biden right now. And just to give you guys a little bit of background, I visited the University of Michigan when Robert was working there, and they have a basically an institute called the Transportation Research Institute, which Robert was a part of, and they have a beautiful thing called M-City, which is geared around kind of autonomous vehicles. So they got buy-in from many different car companies to kind of build this sort of autonomous city. And once I saw this, I was like, oh, this is really awesome. And I sent Andrew to visit Robert, and this project started. So, and Andrew spent a week there and said he loved it. So this project really started from sort of going there and seeing this M-City, and we started to think about autonomous vehicles in a queuing context. So just to give an overview, so I'm going to talk a little bit about teleoperations, what exactly they are. I'm going to introduce kind of a queuing model for this teleoperations center, and more or less we're going to develop some theories to understand these queues that arise in these teleoperation centers, and we'll talk about some data that we had and apply it to staffing these teleoperation centers. And I'd like to mention that much of the sort of theory that we develop here is not only kind of useful for teleoperations, but it's also useful for kind of any kind of system that sees large batches. And so let's get started. So this project actually was first started by thinking about or responding to an accident which unfortunately killed a passenger, Elaine Hirschberg, after an Uber vehicle hit her on the street. So what was interesting is that she was walking across the street here, and the vehicle did see her roughly about 6 seconds before it eventually hit her. And what was interesting is that she was walking across the street with a bicycle. So you could see actually in the NTSB report, the car was sort of unsure whether it was a person. Sometimes it was thinking it was a person. Sometimes it was thinking it was a bike or some other object. And it eventually hit her. Another part of the story is that there was what we will call an in-car safety driver. So there was a person inside the car that in the event of something sort of they see something may happen or the car sort of fails, this person would be able to take over. But actually you can see, I won't show the video, but there is a video online you can check out. You can see actually the in-car safety driver was actually on their phone watching Hulu. So obviously in-car safety drivers are not necessarily the best. And they can be useful, but obviously if they're sort of lulled to sleep by the quality of the vehicle, then they become a little less useful. So just to give you guys some context behind autonomous vehicles, well, they're coming, they're already partially here. We already see many of them kind of on the road, especially on the West Coast in the United States, mainly in Arizona, California. And as I mentioned, M City has some operations actually in Michigan. And the whole goal here, obviously, is to have autonomous vehicles to eventually be sort of safer, smarter, and better sort of sustainable transit for people. So if I don't have to drive from Ithaca to New York City, then I can actually write more papers, I can do more research, I can actually contribute to society in a greater way. And so what we're trying, or what many companies, car companies are trying to do, is make sure that this sort of autonomous technology is ready for deployment and effectively change the way that our society functions. You can think of Uber really, even though they recently sold their autonomous vehicle fleet, they would benefit tremendously from autonomous vehicles. They can effectively get rid of the highest part of their cost. And this is also true in truck driving. If you could remove the person who drives the truck, we save sort of significant savings from those costs. So there are sort of different levels of driving automation. And so currently, I would say that we are sort of in level 4. And these level 4 means that we have some automated features, but the question is, can you actually drive in all kind of conditions? And that sort of distinguishes really the difference between level 4 and level 5 is that level 5 really is you can drive in all conditions. And I can tell you from living here in Ithaca, I don't think many of the autonomous vehicles will survive here, which is the reason why they've sort of been test driven in many places where there isn't the level of snow and sort of complications as you might have here. One actually important thing that is very interesting here is that as an autonomous vehicle uses kind of sensors to kind of tell what's on the road, etc. One of the sort of difficulties is actually the snow, because it will cover the lane sort of partitions on the road. And so it's unclear where you actually should be driving in situations like that. The other thing is that since it also uses sensors, the way that the sensors actually sense the environment changes according to the weather conditions. So you can think about, well, when it's raining, you're actually getting feedback from the rain particles as well. If it's snowing, you're getting feedback from the snow particles as well. And so that actually will change the way that the vehicle actually will engage with its environment. So understanding how the weather environment actually plays a role in the sensing is critical as well. So like I said, we sort of reached level 4, and we've begun sort of testing these vehicles. And Waymo and Uber, Waymo sort of on the Google side, and Uber have begun sort of testing these vehicles on the road, and so far they've done a pretty good job. Some of the accidents that we've seen with these vehicles have actually been caused by human drivers themselves. So they've actually pretty much have done a good job on the road. What was interesting is that there was a recent report done now I'm blank. Oh, done by Rand, actually, the Rand Corporation, to understand when we would actually reach level 5. And this was sort of done with a statistical perspective, trying to figure out how many miles would these companies have to drive until we have kind of confidence that we could drive in any kind of scenario. And so there were many different situations given, but just thinking about if we have to drive 11 billion miles or roughly 500 years, that's really a long time, and we don't necessarily envision, certainly that's probably not in my lifetime. And so we certainly don't envision that we want to get autonomous vehicles right in 500 years. We're hoping to maybe get this right in the next 10 to maybe 20 years. And so this sort of gives you a sense that like there is some concern that we actually never reach this sort of level 5 where cars can drive anywhere. Even the Waymo CEO perhaps is also a bit skeptical that autonomous vehicles will be able to drive in all conditions, but perhaps we can drive in reasonable conditions, and that be okay. So what's holding us back from being able to sort of implement this autonomous vision? One major thing is that there are what we call unknown unknowns, or edge cases, and we kind of don't know what we don't know. So that's kind of the main thing that's holding us back. I think obviously, if you put the car in snow and like the car slips or stuff like that, we kind of know that it's harder to handle vehicles in those kinds of conditions. I even know that from driving myself. But you may not know how the car itself will respond to those various conditions. And so when the vehicles actually encounter these edge cases, this forces something, and this will be a common term in this talk, this forces something called a disengagement. So the disengagement means that the autonomous vehicle will suspend their autonomous operation, and ideally someone else takes on this operation of the vehicle. So what can be done to actually sort of not hold us back and actually get this, sort of realize this autonomous vehicle vision? One of the solutions, which I mentioned earlier, was this sort of in-car safety driver. So it means that someone is already in the car and they're ready to sort of prepare to take over. And what I mean by they're in the car specifically to watch out for any situations. But I've already given you a situation where the in-car safety driver actually was not as useful as we would have wanted to be. And one of the reasons is that the vehicles are pretty good at driving. And so this sort of gives the perspective of the in-car safety driver that the vehicle is reliable and safe, and they may not be as ready when something actually happens. And so the other thing about the in-car safety driver is that this is a one-to-one pairing with the vehicle. So if every time we have an in-car safety driver, this is no different than really ordering an Uber right now. And so is there a way that we can sort of unlock this potential of autonomous vehicles and do a bit better and not necessarily have this one-to-one pairing? So one of the proposed solutions that's currently being adopted across the country in the United States is basically a teleoperation system. And in these teleoperation systems, we have things called remote operators, which is sort of an alternative to these in-car safety drivers. And so what happens here, this is done by a startup called Designated Driver. And you can see this person here has access to this particular vehicle. And the case that this person, or the vehicle that the person is in, suspends its autonomous mode. So you can see that the vehicle gives different perspectives, and you also have a way to see where the vehicle eventually would like to go. And so this person can actually take over if the vehicle sort of suspends its autonomous modes, or disengages its autonomous mode. So this is kind of one potential idea of solving this situation where we have sort of many in-car safety drivers. Once again, this is sort of a one-to-one pairing. But these remote operators can just basically work when they're called upon. And so we'll talk a little bit more about that as we go. So this is kind of one picture of our proposed solution. And if you think I'm crazy for suggesting this, maybe I am, but the United States is actually basically mandating teleoperation now. So there are several states. So the states that are in orange here, you must have a teleoperations kind of system set up to operate these autonomous vehicles. And in other states, so the states in this sort of teal color, still they have an in-car safety driver that is required. In some states, there's no regulation whatsoever. I mean, I guess in these states, there's probably just potatoes and Idaho and various other states. So there's not much you can hit in those states. But and then in other states, teleoperations is a legal thing which you can do. So this picture is constantly changing. And like I said, Michigan is one of those places, which is one of the reasons why M-City actually can operate. And so this is a changing picture, and it's moving towards many states sort of requiring this teleoperation systems for these autonomous vehicles. So here's a sense. So there are lots of companies that are getting involved with designing these teleoperation center. So Designated Driver is one of them, and I'll talk a little bit about Autopia and what they're doing as a player in this particular market. But nonetheless, there's lots of different companies that are getting involved. Nissan also has a very good or is now starting their teleoperations center as well. So in addition to that sort of perspective where we have this sort of remote operator, so that picture that you saw from Designated Driver, there's also a notion of teleoperations where you have sort of artificial intelligence sort of gauging what's going to happen in the future. And so here, what you see is like someone is driving a car and it wants to get to some destination. And what you're sort of drawing out here is like, what is the best path for the car to take to get to that particular destination? And so one of the things that people are interested in is having human beings navigate vehicles through different scenarios. So this is pretty important because what effectively the humans are doing are training various artificial intelligence systems. So basically, okay, this person wants the vehicle to get from point A to point B. Maybe there's some barriers that the person can see here from the vehicle. And so what this person is doing here is actually sort of helping the AI systems train themselves so they can actually sort of learn from these sort of unknown situations. And so these humans here are actually helping sort of train these systems. And so this is also another perspective that teleoperations offers. And as I mentioned, Autopia calls this sort of advanced teleoperation. So these types of people, these sort of remote operators as well, are helping these AI systems actually learn better. And ideally, this information is embedded into the vehicles, which actually help them drive and handle these unknown situations that they have. There's also another type of teleoperations. And so imagine a vehicle actually is traveling, and more or less there's sensors on the road or on the vehicle, and those sensors can kind of look ahead. And what some teleoperation systems envision is that this vehicle can actually, let's say, look ahead like 15 seconds. And if it senses that something is, wrong or uncertain ahead, it will actually send information back to our teleoperation center. We're thinking that we have 5G up and running and no issues, but this will send information back to our teleoperation center. We have a group of people who look at these scenarios and sort of gauge whether the vehicle should continue to go, or maybe it should actually disengage kind of safely. This group of people kind of, you can say yes or no, the vehicle should disengage or not. And basically we're crowdsourcing their information on whether to sort of continue on with the vehicle. This sort of just-in-time, what we call just-in-time crowdsourcing, can actually be done in about 3 to 5 seconds, depending on your wireless connection. And this has been explored quite considerably at the University of Michigan by some colleagues of ours. And so one question is, in this context, how many people does it take for us to run this teleoperation system if we had to do this sort of just-in-time kind of crowdsourcing to ensure that the vehicles that we're operating are safe and reliable? So I'm happy to stop here for a second and see if there are any questions. So what I'm going to do sort of for the remainder of the talk is talk about these different kind of operations via teleoperations and sort of connect those to various queuing models with large batches. But I'm happy to stop here and see if there's any questions before I continue on.
I have one very small question,
Yes.
which is when they require these teleoperations, do you even require people to be in the vehicle? As in, can you have like a fleet of lorries driven with no one in them, and then there's just a teleoperator? Is that legal?
That will depend on the state, but yes, that is perfectly fine to have no one in the vehicle. So, I mean, an ideal situation is effectively to have these with trucks. So, you can imagine sort of a fleet of trucks. Maybe there's a person at the front, and that sort of in a truck that's at the front, but one does not necessarily have to have that. So I got a question from Harsha. It says, does each teleoperator manage multiple vehicles? So that's the idea, is that it's sort of like on demand. So you can think of this more or less as like a call center. So if I go back for a second, once this vehicle says, okay, I've encountered an uncertain environment, maybe, so once I've encountered this uncertain environment, a call is sent out to one of the teleoperators to kind of check. So if you have a vehicle disengagement, then a teleoperator will be called. So in many ways, it's kind of, you can think of it as OnStar, but it's not exactly that. Like OnStar generally is when someone hits a button or it actually detects a crash. But here we're not actually trying to get you to crash. We actually want you to not crash, and we're trying to sort of look ahead in that context. So the idea is that you should be able to handle, like you will handle one person at a time, but you can sort of be responsible for multiple vehicles at a time. So another question is, can you elaborate further on crowdsourcing in this setting? So like I said here, the crowdsourcing, basically this is sent back. So information from the vehicle is sent back to our teleoperation center. These people are trying to decide whether this vehicle should continue on. Like a sort of very jokingly example Andrew and I came up with was, suppose a vehicle is along a highway, and the vehicle is trying to determine whether a white plastic bag is, a paper bag, or is it a kid in a ghost costume. So so in some sense, this imagine now this information gets passed back to the teleoperation center. These people sort of, say you have 100 people, and they all say, okay, well, that thing actually looks like a kid. I can see the feet, and this is a kid in a ghost costume. So this vehicle should actually stop, as opposed to sort of continuing on. And so that's kind of the idea behind the crowdsourcing. It generally, you can actually see sort of far enough ahead to actually do the crowdsourcing, depending on how fast the vehicle is actually going. But if you kind of envision this in areas where you're doing 30 to 40 miles an hour, then it's actually fairly reasonable to do the crowdsourcing ahead. Okay, so now we're sort of reframing this question from how many people does it take to run this teleoperation center to how does one staff this queuing system with large batch arrivals. And there's been a lot of work with sort of batch queuing systems and the single server and the multi-server setting. And there's lots of work by David Yao and others. And in our context, what we're going to do is actually scale the batch size, which is quite different from previous work. So generally, when you see kind of a multi-server kind of health and width scaling, you kind of scale the arrival rate and you scale the number of servers. In our setting, what we're going to do is scale the batch size, and we're also going to scale the number of servers. I should mention that as of like a few days ago, we've come up with a scaling that can combine these things together. And if you want to know more about that, ask Andrew. But nonetheless, we will talk a little bit about what this means. So you can once again imagine that we're going to model our teleoperations as a batch multi-server queue. And just to motivate the model, we can think about, okay, jobs are going to arrive when we have disengagements. And so there's a lot of data actually that exists from many of these companies. So in particular, GM Cruise and Waymo have pretty good disengagement reports. And this is a requirement for actually operating autonomous vehicles in the state of California. So what you see actually is Waymo is kind of ahead. So Waymo kind of leads the industry with, they can do about 11,000 miles per disengagement. So if you think about that in the context of a human driver, a human driver does, I don't know, from 10 to 15,000 miles a year, one disengagement per year actually isn't so bad. GM Cruise is around 5,000, but that's still pretty good in terms of driving as well. So what we're going to do is jobs are going to arrive according to a general kind of arrival process, which can depend on time. And these will represent the sort of disengagements that the vehicle will sense. What's going to happen is that we actually may, because the sort of look ahead assistance and this sort of just-in-time crowdsourcing requires multiple people, ideally we're going to call on multiple different servers at once and ask them for their feedback. And so this will sort of create a batch, and we have sort of a general batch process here. And this will also generate fast service. But in the context of our model, we won't be necessarily scaling the service. It will just be thought of as being kind of a fast service, but not necessarily scaled with the number of people. So, and finally, what we're going to do is scale the number of servers. And the idea here is that, okay, well, the more servers we have, a little bit longer we have to wait for them to come back. But we also need to, the more servers we have, the more safety we have in some sense. We're sort of crowdsourcing more people, and this sort of leads to more accurate responses. So this is kind of the queuing model we envision. And now what we're going to try to do is, can we understand this kind of queuing model and do the standard kind of limit theory for this particular model. So what we're going to do first, and so I'm going to start with the infinite server setting. So we'll consider this model here, and we'll start with the infinite server setting. And this is sort of classic in queuing theory that we start with the infinite server model because it sort of gives us a lower bound. And we'll see later that this model is actually important for constructing our finite server model. And we'll use some results from Josh Reed actually to make that connection. So what we're going to do is we're going to let Q of T be our queue length process. And like I said, G of T will represent our general but possibly correlated and time varying job arrival times. And B of N is going to be our batches of arrivals of a random size, but they grow with N. And G sub I is going to represent our service times. So in general, the probability that the queue length in the infinite server model exceeds some value X is actually less than the probability that Q of C, where C would be a finite server system with C servers, also exceeds this level X. And so, like I said, this infinite server model serves as a lower bound. So I want to walk through just kind of understanding the infinite server setting. So the queue length actually can be written as a double sum. The first sum is over the number of jumps. So that's the number of arrivals to our arrival process NT. And the second sum counts across the batches. So for arrival 1, there were B sub I or B sub 1 people that are needed. And so if we're summing across that, then this is exactly how many people are sort of being or are needed in our particular infinite server queuing model. So this indicator represents, okay, is an indicator that T should be less than or equal to AI plus Sij. So this is basically whether or not the person being used is T actually less than this particular quantity. If it's less than that, we count them in our queue length. And if it's not, then we don't count them. So this is our queue length. And if you actually scale this queue length by n, and you scale the right-hand side by n, you get this expression. And what I'd like to do here is, okay, take this 1 over n. What we're going to do is multiply in the numerator by b sub I of n. And we're also going to multiply it in the denominator. So this is essentially 1. So we've done really nothing. But this sort of helps us think about what's going to emerge as we take the limit. So when we take this limit, we should get something that's close to the CDF, and we'll see that shortly. So it turns out that once you take this limit as n goes to infinity, you're going to get this portion here converges to the tail CDF of the service distribution of t minus the arrival process. And this piece here converges to a random variable mi. And this sort of has a size that's associated with the batch size, but is scaled by n. And this actually turns out to be something called a shot noise process. So what we can show is that in this infinite server model where we scale the system with large batches, we actually get a shot noise process out in the limit. And I should mention that this thing actually is random, and it depends on the arrivals of your system. So keep this in mind as we move forward, that the infinite server system, when we have large batches and we have, in this case, is an infinite number of servers, and we scale the system by n, we actually get a shot noise process out in the process. And shot noise has a history of emerging in the physics literature as well. So just to give you guys a sense of what's going on in this particular process, what we have here in blue is this scaled queue length process, and the scale here, I believe, is n is equal to 100. So what we have is our scale queue length process and our actual shot noise, and it seems that they are basically the same, more or less. And so this results into our first kind of result, where as we set n towards infinity, we can show that this batch queuing model actually converges to the shot noise process. And like I said, it's important to see that the arrivals, like this eventual shot noise process, like nothing happens with the actual arrivals themselves. So that actually stays the same, and this is still kind of a random process. So now that we know that as the batch sizes grow large in this infinite server setting, that we converge to a shot noise, a question is like, can we actually use this to get a better understanding of our multi-server model, which is kind of classic. So what we're going to do now is we're going to represent the multi-server model into two pieces. So the first piece is going to be exactly the infinite server piece. So we still have this double sum of all the jobs according to the arrival time and the service that they need. And so this is sort of the infinite server piece here. And here's a piece where the jobs may also have to wait. So we're calculating also, well, does your job actually need to wait as well? And so this waiting distribution here, Wij, is the waiting duration of a job J that occurred in batch I. So you can think of this as jobs that start immediately, so on the left, and then on the right we have jobs that have to wait. And so this is our setup. So a key ingredient to studying this multi-server model is this sort of key lemma. And what does this thing say? Well, it says, okay, if I count up the arrivals and their subsequent batches, and I take the difference between the tail CDF of the service time distribution with the arrival minus its waiting time minus just the arrival. This piece here is equal to the integral of the queue length minus the number of servers, take the positive part of that, and I'm integrating with respect to the service time density. So this actually is a generalization of Josh Reed's sort of celebrated result in multi-server queues, but we extended this result to the batch setting. And what's nice about this is that you can, if I go back, if I can think about this infinite server piece and this piece where jobs have to wait, well, the jobs that have to wait are generally given here. And if I operate an infinite server system, and for the jobs that actually do have to wait, I can basically integrate the service that they're experiencing from the infinite server setting. And so if I can actually add that back to the system, then I'm actually capturing kind of what's going on in the multi-server setting. So that's kind of what this result is doing. So we can further kind of decompose the system. So I represented the queuing system from before as this is the stuff that starts immediately. So jobs that start immediately. And then these are jobs that have to wait. This is exactly that key lemma that I had before that said that, okay, this integral here is equal to this double sum of the tail CDFs, so the service times. And so what we're going to do is now sort of match various components and try to show that various pieces are zero by martingale arguments or by sort of taking limits. So so what we have here is this same integral here, or sorry, double sum here, where the jobs that start immediately, we still have our integral from before here. And I've split each one of these terms up and I've matched it with a subsequent indicator that comes from this term. So keep in mind, there's actually two kind of inequalities here. And so one represents, okay, is T in between this time and the time that includes the waiting time. So I take each one of these indicators and match it up with our tail CDF here. So this is kind of decomposing the queue a bit further. And now what we're going to do is take limits. So I scale both sides by 1 over n. And what you'll see is that this term is going to go to shot noise as we've seen before. This term is going to go to 0. So this is, remember, this term also converges to a shot noise by our result before. And so it'll match exactly with this expression here. So this term goes to 0. Similarly, this term is also going to go to 0 by using some martingale difference argument. And last but not least, this term here is going to converge to the shot noise minus the value C here integrated against the service time distribution. So it turns out that this process here goes to something called a generalized storage process. So we can show that our queue length, when we have a multi-server queue length with our batches being scaled at the same rate as the servers, this converges to a storage process. And the dynamics are given by this expression here. So now that we have this particular expression, the question is, how can we actually use this in practice? So in the exponential service setting, I'll skip through this in the interest of time, but one can show actually that in the exponential service setting, the storage process, you can actually get a differential equation that basically describes the dynamics of this particular storage process. So if you take the time derivative, you can show that, okay, during times where there are no arrivals, well, the storage process is draining at this particular rate. So if it's above the level C, well, it's going to drain at rate mu times C. And if it's below C, then it's going to drain as mu times the level of the storage process. So this is kind of one example when the service time density is given by an exponential distribution. You get this nice sort of differential equation kind of form. So let's do kind of an example, sort of exploring this impact of the large batches. In this particular case, we have n is equal to 5, and this sort of gives you a sense of what the process actually behaves. So here we have the queue length, which is scaled by our value n as well. And as we scale n, we start to see this thing converge to what we think of as our storage process. And if we scale it a little further, you'll see, okay, we have a jump according to an arrival, and the system sort of decays exponentially as it's below our level C. And what you see above our level C, it actually decays linearly. So this is mu times C, the decay rate, and below it starts to decay exponentially. So you can see that this queue length, as we start to scale it with our large batches, looks more and more like our threshold storage process. So how does this actually help us staff the queuing system in this context? So just to give you a summary here, this is going to be the number of servers that we're going to use. And so if you think about your storage process, well, you're going to set this level C for some particular performance measures that you might want to see. So this is the level C that we would want in our storage process. And so if we want to make sure that maybe our queue length does not exceed some level C times n, well, we can use the storage process and calculate the probability that the storage process actually exceeds this level C. So in this context, we're able to use the theory from the storage process and extrapolate that back to the queuing process, which is a much more difficult kind of object to handle. There's a sort of old theorem of Brockwell and Davis, among others, which talks about computing the distribution of the C threshold storage process when the service time distribution is exponential. So you actually can get a closed form integral equation for computing that distribution. So one can use this to effectively staff our queuing system by using the properties of our storage process. So our goal in terms of, like, if you were to sort of explain this in a course, is one would set a probability for the storage process equal to some value epsilon. We don't want our storage process to exceed the level C with more than probability epsilon. And so once we find the C that actually gets us roughly epsilon, we can staff our corresponding queuing system with C times n, and that should do a good job. So what we're going to do now to sort of kind of wrap up much of the talk is go back to some of the data sources that we've used before, by using some of the disengagements to get a sense of when arrivals occur, and also using some information from the National Household Travel Survey, which gives us information on how people actually travel, how long they travel, how much they travel, for what distances they go. And we're also looking at some urban taxi data sets to get a sense of where people are kind of moving. So one of the interesting things here is that we sort of derive a sense of how many operators do we actually need. In this particular case, we're staffing the levels to achieve a 0.001 exceedance probability. And what you see is as I increase the number of vehicles, if I were using the in-car safety drivers, this would be a 1-to-1 pairing. So it'll be just a linear rate. And as you can see, okay, this is sort of sublinear as we start to add more and more vehicles. What's interesting here and what's the most important message of this particular slide is that as we increase the number of the batch size, so let's say the batch size here is 250, and if we increase that to 500, precisely as I double the batch size, I also double the number of operators. So the number of operators is linear with respect to the batch size itself. So in some sense, like batches actually cause more issues, and there's actually more variability there. So like I said, one of the observations is that the staffing level is sublinear in the number of vehicles. So it's growing sublinearly in terms of the number of vehicles. However, our staffing level is exactly linear in the batch size. So if I double the batch size, I'm going to double the number of operators that I need. And that sort of makes sense that, okay, if I double the batch size, every time that I'm calling, I need sort of double the number of people to operate the system. So what we did actually in this work is try to give a sense of how many operators would you actually need in sort of these large metro areas across the United States, and also give a sense of what their actual utilization is. And so in this particular case, when we staff for n is equal to, let's say 1,000, so 1,000 people are needed per call, which seems a little extreme, but we just wanted to get a sense, we would need roughly 27,000 people to handle let's say 500,000 vehicles in the New York City metro area. And so this sort of is a significant drop off from using 500,000 in-car safety drivers, which it just doesn't seem practical from that point of view. But this gives you a sense of how many people you would actually need to handle a large kind of metro area at a safety level of 1,000 people per call. Maybe we can get away with 100 or somewhere in there, but this sort of gives you a good sense of that we don't need 500,000 people. We only need kind of a few thousand people to kind of operate this in a large metro area. What's nice about this, and I like to mention to a lot of people, is that often sort of advancement in technology is detrimental to job growth. But I think one of the things that we want to sort of say here is that we can actually operate these vehicles and actually create some jobs in the meantime. So this sort of gives a sense of how many people you need in these metro areas. So like I mentioned, we want to get to level 5 for autonomous vehicles. They have sort of tremendous value, but many people don't see this as attainable just yet. And so teleoperation systems have basically been proposed to assist these autonomous vehicles in ways that we currently don't have. And so this particular work has explored how many people do we actually need to operate these teleoperation systems. And just as sort of some key insights from this work, we talked about large batch arrivals, and these things sort of behave like storage processes. And we see that batches actually have a stronger effect on service systems than the arrival rate does. And we believe that these teleoperation systems, as they're actually being deployed now, Robert can actually tell you a lot about that, since he's now in the Department of Transportation. But actually, a lot of companies are deploying these now, and they are in need of our insights. One other thing is I mentioned that earlier on, that much of this work is not only useful for autonomous vehicles, but it's also useful in cloud computing systems. It's also useful in modeling COVID on our campus. The sort of COVID example would be, one of the interesting things is we were doing kind of surveillance testing on students to see which students had COVID, et cetera. But once they actually, if they had a positive test, they would all be put into our campus hotel. And if you think of our campus hotel as kind of a service system, once all of the students were sort of, deemed that they actually had COVID, they would go and basically batches. So every day we get a report, how many students have COVID now. And then, when there was a big party, there was actually a large batch of students that got COVID. And so this sort of analysis actually was useful for understanding, well, do we actually need to go out and buy some more hotel rooms for students who are going to get COVID? So there's lots of different examples of where this work can be useful. And I want to leave sort of the talk and sort of end on a note of this second bullet here, is who is left out in the vision of an autonomous future. And often we sort of get very excited about kind of technology, the sort of ease and the benefits that it may provide. But one of the more important things, I think, for our community to think about is, as we kind of build these kind of systems, who's left out? And I'll give you one example. Andrew's probably sick of this example, but I do think it represents an important example nonetheless. Is, so if we have autonomous vehicles up and running and they're running perfectly, and let's say we envision a society where we never ever get into an accident, it turns out that a significant portion of donors, sort of organ donors, actually come from car crashes. And so certainly we don't want people to get into car crashes, but this actually significantly changes the organ donation space if we get autonomous vehicles sort of perfectly. And certainly, like I said, we don't want people to get into accidents. But it makes you think about what actually changes, what things are different when you have kind of a full autonomous future. And so, this is sort of an extreme example, but I do think it is important for our community to kind of think about what does change when we sort of unleash a new technology. So I'll stop here, and I'm happy to answer any questions.
Okay, I'll quickly thank Jamol. So thank you. Yeah, if there are any questions. I had a couple of modeling questions whilst people might be
sure
their questions. So I didn't quite see the rationale for why the batch sizes had to be large. So that's simply to increase the response time, is it? Or is it, and is it the case that you're thinking that there are a lot of sort of people passively who might be available in order to take the request, but they might not be concentrating, and so you need to reach out to a large number of people.
That I think actually the latter part is one potential thing, but we're also thinking that if we're doing this sort of large crowdsourcing, then of trying to get information from people in terms of like what they actually see, then we're thinking that the more people we actually have, the more reliable our information is going to be. And so that's only one piece. Like I said, there's kind of three pieces here. Like there is this sort of look ahead behavior. There's also the remote operators themselves. And so I actually would think of that as like a separate model, but I do think the large batches here under this sort of crowdsourcing example.
Okay, I see. So it's more related to the training and reacting to in order to train these vehicles, essentially.
Yes.
Rather than the kind of emergency operation thing, because that was really leading into my second thing. Because if you want to really, if it was an emergency thing, you wouldn't want any queue in your system. So you'd always want tree capacity, and so it's sort of more of an Erlang type of system rather than
yes. So one of the, I mean, since we're here, one of the interesting things we have been thinking about, since Andrew and I also work on Hawk's processes, is that if you were to like get into a situation, imagine like we're experiencing this storm on the East Coast. If a tree sort of fell down on a highway, it's not only that car number one would see this tree and say, okay, I need to do something different. It's also that the cars behind it would also see the tree and they also need to do something different. So in that case, there is this sort of like once one thing starts, there is sort of this self-exciting behavior to like actually get access to someone to help you in this situation. And so we've been thinking about kind of, although this is sort of general to handle things like that, we want to sort of explicitly really understand different behaviors when this might be like kind of a self-exciting process. And so it naturally sort of self-excites in that setting. The other thing is that you also see this when you think about if you're in an area of uncertainty, perhaps vehicles behind you will also be in an area of uncertainty. And so you might see, multiple cars kind of make a request at the same time. And seemingly this may not seem like a batch, but if you're on a large enough highway or a large enough road, multiple cars sort of making the same request can experience like a batch. So you may think of it as like a self-exciting process, but if you scale this self-excitement and make it happen in very short bursts, then this also looks like a batch. And we have some results about that. So
I mean, in that kind of setting, you could imagine something like where the immediate cars that arrive need a very quick response time, but then there's this kind of tail behind them of cars who it's going to happen to. So you've got like a lower response time requirement for those as well. So I could imagine some sort of Erlang queue with a priority and the Hawks process.
Andrew should so in our paper, which I beg the community to accept our paper, but in our paper actually we actually have some results about this for an Erlang type model as well. So so it's not only just the infinite server, the multi-server, we actually have like a blocking storage process too. And so you get a different process in the end, which sort of rejects anything that exceeds a particular threshold. And we actually have some results on how to actually compute that that sort of blocking probability in our paper actually.
Any further questions? Okay, well, if not, I'll thank Jamol again, and we'll probably, turn off all the recording, and if people want to ask some questions a bit more informally, then we can do that. So
Sure.
thanks again, Jamol. I'll stop the live stream as well.